Welcome students. Myself GB Patel, lecturer in mechanical department, PPMP Polytechnic. The subject is thermodynamic. Subject code is 3331902. Today we are going to discuss the Otto cycle. The objective of this video is to derive the air standard efficiency of the Otto cycle. So let us derive the efficiency of the air standard efficiency of the Otto cycle. You can see here the Otto cycle on the PV diagram and on the TS diagram. There are four processes of the Otto cycle. Process 1 to 2 is a reversible isentropic process and it's a compression process. Reversible isentropic process means adiabatic process, and here compression work is there. So compression work is done on the cycle. Process 2 to 3 is an isochoric process and heat is added during this process. Isochoric process means volume constant process. That is why you can see here volume V2 is equal to V3 on the previous PV diagram. You can see here V2 is equal to V3. Process 3 to 4 is again reversible isentropic process. It's an expansion process. So expansion work is delivered during this process. Reversible isentropic means adiabatic process. Process 4 to 1 is again isochoric process. During this process, heat is rejected. 4 to 1 is isochoric process, that is why volume is constant and V1 is equal to V4. You can see here on the PV diagram. Okay. Same cycle is presented on the TS diagram. Compression ratio. Okay. What is compression ratio? It's a ratio of V1 divided by V2. Volume V1 divided by V2. What is volume V1? It's a volume before compression process. What is volume V2? It's a volume after compression process. And as you can see here, V1 is equal to V4. So we can write V1 is equal to V4 and V2 is equal to V3. So V2 is equal to V3. So compression ratio RK is equal to V1 divided by V2 or V4 divided by V3. We know the definition of air standard air standard efficiency of the cycle is 1 minus Q rejected by Q supplied. You can also see during this cycle there are two type of a heat interaction. One is heat supplied, which is QS. Another is heat rejected, which is QR. Heat supplied occur at the isochoric process 2 to 3. Heat rejection occurs at isochoric process 4 to 1. So during isochoric process, whatever the heat interaction is there, that can be calculated by CVDT or MCVDT. Here we assume that the mass of the gas is 1 kilogram. So we only use the CVDT. So instead of QR, where is the QR? During process 4 to 1. And 4 to 1 is isochoric process. That is why we can write CVDT. So here CVDT, which temperature? T4 minus T1, because QR is here. QS, where is QS? During process 2 to 3. It's again isochoric process. So that can be calculated by CVDT, which temperature range? T3 minus T2. So air standard efficiency of Otto cycle is equal to 1 minus CV T4 minus T1 divided by CV T3 minus T2. So CV get cancelled. So the equation is reduces to eta Otto is equal to 1 minus T4 minus T1 divided by T3 minus T2. Say equation A. Now consider process 1 to 2, which is reversible isentropic process. You can see in the diagram 1 to 2 or here. It's a reversible isentropic process, means adiabatic process. So for adiabatic process, you can write TV raised to gamma minus 1 is constant. So process is 1 to 2. That is why we can write T1 V1 raised to gamma minus 1 is equal to T2 V2 raised to gamma minus 1. That is why T2 is equal to V1 divided by V2 raised to gamma minus 1 into T1. Okay. And as we know, V1 divided by V2 is a compression ratio. this V1 divided by V2 is a compression ratio. So instead of V1 by V2, I can put RK. So V1 by V2 is it's a RK raised to gamma minus 1, and that T1 I put on the left hand side. So this equation become the T2 divided by T1, and instead of V1 by V2 I put RK, so it's RK raised to gamma minus 1. Say equation number 1. Similarly, consider process 3 to 4, which is again isentropic process, reversible isentropic process. See on the diagram, this process 3 to 4, isentropic process 3 to 4, isentropic process. Reversible isentropic process means adiabatic process, and for adiabatic process you can write Tv raised to gamma minus 1 is equal to constant. That is why here process is 3 4. So T3 V3 raised to gamma minus 1 is equal to T4 V4 raised to gamma minus 1. So I take T4 on the left hand side and V3 raised to gamma minus 1 on the right hand side. So equation become T3 divided by T4 is equal to V4 divided by V3 raised to gamma minus 1. And as we know, V4 divided by V3 is RK. So instead of V4 divided by V3, we can put RK. So instead of V4 divided by V3, I can put RK raised to gamma minus 1. Now see the equation 1 and equation 2. This equation 1 and this equation 2. The right hand side of the both equation is same. It's a RK raised to gamma minus 1. You can see here. So equation 1 is equal to equation 2. So I can write T2 divided by T1 is equal to T3 divided by T4 is equal to RK raised to gamma minus 1. So equation 1 is equal to equation 2. That is why T2 divided by T1 is equal to T3 divided by T4 is equal to RK raised to gamma minus 1. Consider these two step. Consider these two terms. Take the T4 on the left hand side and uh, T2 on the right hand side. So I can write T4 on the left hand side and T2 on the right hand side. Exchange it. Mathematically, it's okay. So T4 divided by T1 is equal to T3 divided by T2. Add minus 1 on both sides. Mathematically, it's okay. So you can write T4 divided by T1 minus 1 is equal to T3 divided by T2 minus 1. So you can write T4 minus T1 divided by T1 is equal to T3 minus T2 divided by T2. So T4 minus T1 divided by T1 is equal to T3 minus T2 divided by T2. Same step. And this T4 minus T1 as it is, the T3 minus T2 I take it's on the left hand side and this T1 is on the right hand side. So I can write T4 minus T1 divided by T3 minus T2 is equal to T1 divided by T2. And what is T1 divided by T2? Say equation 1. T2 divided by T1, it's RK raised to gamma minus 1. So reciprocal of this T1 divided by T2, it's 1 upon RK raised to gamma minus 1. So I can write T1 by T2 is equal to 1 upon RK raised to gamma minus 1. So instead of T1 by T2, I can put here 1 upon RK raised to gamma minus 1 from equation 1. As we see this equation, T2 divided by T1 is equal to RK raised to gamma minus 1. So T1 divided by T2 is equal to 1 upon RK raised to gamma minus 1. Okay. And substitute this value in the equation 1. What is equation 1? This equation. And this value T4 minus T1 divided by T3 minus T2. That is 1 upon RK raised to gamma minus 1. This value in equation 1. Sorry, equation A. In this equation. So here you have to put 1 upon RK raised to gamma minus 1. So 1 upon RK raised to gamma minus 1 here. So I can get the final equation. Air standard efficiency of the Otto cycle is 1 minus 1 upon RK raised to gamma minus 1. Thank you.